Okay, so I'm just gonna go over this real quick, just kind of explain how voltage drop works, how this equation works. There's a few different ways to do it. This is the way I'd like to teach it at first. It's a good, reliable way to do it. So this is the equation for voltage drop. The way I always remember this is Edzilla kills 2 CMA. I had my teacher in college, his name was Eddie, so we always called him Edzilla, so that's where that came from. So ED is your voltage drop. K, that's going to be a constant number that you always use, whether the conductors in the circuit are copper or aluminum. These are the two numbers. So it's 12.9 for copper, 21.2 for aluminum. I is the current for your circuit. L is the length of the circuit. And then times 2, this is going to be a single phase circuit that I'm doing first. That's going to change for 3-phase, but I'll show you that real quick at the end after we do this. And then you multiply all those across, and then you divide by the CMA. That's the circular Mills area of the conductor that you're proposing to use in this circuit. All right. So let's go through one. Let's say you got a circuit that's like, let's say you got a 120 volt circuit. It's 20 amps, and I don't know, let's say you got a chicken coop that you're running power out to. So 20 amp circuit, 120 volts, and it's 275 feet away, okay? So you just plug these numbers in to the equation. So let's say it's copper conductor, right? So you're gonna have 12.9, we got that from our constant up here, times 20 amps times 275 times 2, because it's a single phase circuit. And then you divide by the circular Mills area. So you find the circular Mills area in the code book. You look at that, you find it. So for a number 12 conductor, because it's a 20 amp circuit, we're gonna assume that it would be a number 12 conductor. You got 6,530. 6,530 CMA. All right, that's our equation right there. So obviously we simplify it. So you start off, remember PEMDAS, the order of operations. 12.9 times 20 times 275 times 2 is 141,900 divided by 6,530. Right? See how that works? All right, you with me so far? All right, so now you just take that 6,530. So that comes out to, you do this, you get 21.7 volts. So we've done the equation. This is what our voltage drop would be, right? We have 120 volts at one end. At the end of that wire, if you take a voltmeter and measure it, you're gonna be, what is it? 198.3 volts, right? So you're gonna lose 21.7 volts. Just, that's the resistance in the wire, right? That's gonna cause that voltage drop. So we do this calculation to make sure that we don't lose voltage. We're allowed to lose a certain percentage, right? And that gets into some other stuff in the code. I'm not really gonna get into that right here. I just wanna show you how this equation works, right? So that's for a single phase circuit. Once again, K times I times L times 2 divided by CMA, right? Your K is 12.9 for copper, 21.2 for aluminum. You do all this math out, and that gives you what your voltage drop is going to be across that circuit. So that's for single phase. Let's get rid of this. So for 3-phase circuits, it is just a little bit different, but not much. All right, instead of multiplying times 2 at the end, you just do 1.73, because that's the square root of 3, okay? So now let's say we have a, oh, I don't know. Let's say it's a 3-phase 208 circuit. So 208 volts. Let's say it's a 30 amp circuit. Okay. And it's, oh, I don't know, 320 feet away, right? Copper conductors, we'll stick with that theme. So 208, 30 amp, 320, yeah. So, and obviously if it's 30 amps, we're gonna assume that it would be a number 10 conductor, right? So number 10, copper. I'll fix that, that looks a little, oh, I tried to fix it and I made it worse. Here, number 10, copper, boom. All right, so now once again, we just plug our values in, right? Copper conductor, so 12.9 times 30 times 320 times 1.73, all right? So once again, we find the value, we find the circular Mills area of a number 10 conductor. Let's see, that is 10,380, 10,380. All right, so now we do this math. 12.9 times 30 times 320 times 1.73. Let's see, I got 214, 243 divided by 10,380, right? So now you do that math, divided by 10,380, we get 20.64 volts, right? So once again, we would have 208 on one end, and then we would have 20.64 volts less on the other. Okay, I'm not going to do that math in my head right now, but you can imagine it's more than what's acceptable, right? So, and there's different things you can do. Like I said, you can rework this equation a few different ways. This is just like bare bones, like introduction, how to do voltage drop calculations really quick. But yeah, there's a whole range of topics that kind of can split off from this. A whole bunch of rabbit holes you can go down, you know, where the K factor comes from, what the, you know, percentage losses are that we're allowed to use, how to change it around so that instead of, you know, if we know what our allowed voltage drop is, you know, we can just change the equation around so that we can just find the circular Mills area that's required for the conductor for that circuit. There's a whole bunch of different ways you can rework this, but I just want to keep it simple. Just like I said, this is bare bones. So yeah, hope it helps you out.